let's get started with today's stuff. I can find a piece of chalk with some actual length to it.
Are we just on this chalkboard?
I guess so. I think I'll roll over to here to the whiteboard when we're proving all this, because I just wrote out what we need to prove. I didn't do the proofs on those. Okay, so let's recap from last time some basic terminology, because we gotta get to the point where this terminology doesn't confuse us anymore. It just makes perfect sense. So first off, first review, proposition. What's a proposition? Proposition. Let me propose something.
A statement that's either true or false?
Yeah, it's something that's either true or false. For programmers, it's the same thing as a Boolean. Oops. Same thing as a Boolean. Something that's true or false. The sky is blue. That's a proposition. X is greater than 2. Is that a proposition?
No.
No, we can't call that true or false.
Right.
So that's not a proposition. Okay, so proposition, something that is either true or false. One and only one of those two things. Takes on the value t or the value f. Okay, what are our logical operators?
Like just list them?
Operators. Yeah, what are they?
And or.
Perfect. And or not implies logically equivalent. I'm trying to upgrade you to more modern terminology from what the author uses. Because the author called these things sentences. No one calls it sentence logic. No one calls it sentential logic. They call it propositional logic. And so what he means by sentence, we mean by proposition. The author called these truth functional sentential connectives. Everyone else out in the world calls them logical operators. And so upgrade our terminology here. All right, next, predicate. What's a predicate?
A proposition valued function.
A proposition valued function. It is something that you need to give it a term, and if you give it a term, then it will spit out true or false. This is a predicate. It becomes true if we give it 5. It becomes false if we give it 0. Another example is the is blue predicate. Is blue. That's a predicate. Sometimes we say X is blue to mark where the term would go. X is blue. That's the is blue predicate. If I give it me, it returns false. If I give it the sky, it returns true. Predicates can take on multiple terms. So I could have the predicate X is greater than Y. So now it needs 2 terms to evaluate it. We have a special name for predicates that take 2 terms.
Relations.
Relations. So a special type of predicate that takes 2 terms, relations. And we use that terminology all the time, relation, relation. Okay. So that's predicate. Proposition valued function. Something that you give it a term and it spits out a proposition. The value it spits out is a proposition. Proposition valued. Okay, now a term. What's a term?
Variables or constants.
Variables are constants. Variables, constants. And then there's one more thing we can do with terms. We can combine terms together to create new terms. Using
all I can think of is predicates.
no. Predicates take in terms and they spit out true or false. Is there anything we can think of that takes in terms and spits out terms?
Your operators?
Operators. So we can also use operators to combine variables and constants to make new terms. So this is a term, 3 plus 27 minus x to the power of y.
Oh, right.
That's one complex term. But it's a term, just a bunch of operators and constants and variables. And if you do it in a way that makes sense, then it's a term. And we had, when we first talked about terms, we talked about the concept of, I can't remember what the author called them, something like atomic terms. And then he gave the rules for how we can build more complex terms from atomic terms using operators. Okay, so that's terms. And then finally, quantifiers. What are our quantifiers?
The there exists and for all.
The existential quantifier and the universal quantifier. The there exists and for all. And so there's two ways that we could get a proposition from a predicate. So here's an example of a predicate. X is greater than 2. There's two ways I could get a proposition from that. I could give it a constant, so plug in something like 5, and now it becomes true or false. Or I can bound the variable with a quantifier. And I could say something like, there exists x, such that x is greater than 2. And now this whole thing becomes a proposition. Or I could have said, for all x, x is greater than 2. Now it's false, but still a proposition. It becomes something that's either true or false. So there's two ways we can get propositions from predicates. One is plug in the constants, however many constants it needs. The other one is bound its variables with quantifiers. Those are the two ways that we convert predicates to propositions. Once we convert predicates to propositions, we can then apply logical operators to them. Because logical operators only make sense on propositions. Okay. Good. So there's a quick recap for the logic that we did. Maybe one more thing to talk about before we continue on. Let's remind ourselves of all our different rules. What were all the rules of derivation that we had?
You can introduce a premise.
Premise, rule P. Rule P, that's a rule that we can introduce a premise at any point.
And then there's reductio ad absurdum.
Reductio ad absurdum. That was a derived rule, not one of our initial rules, so maybe we won't put that here.
I don't know if conditional premise is one of those rules.
Conditional premise is one of them. Conditional premise, that's one of them. That's one of the ways that enables us to remove a premise. P says we can introduce a premise at any point. Conditional proof says we can remove a premise under certain conditions. What other rules do we have?
We can use tautologies or introduce them. Rule 2.
Rule T. Rule T says we can replace a line, or we can introduce a formula that is tautologically entailed by previous lines in our derivation. Maybe by just one previous line, in that case it's tautologically equivalent to it, but typically we say this line and this line together logically imply this line. That's the way we usually do it. So that's rule T. Okay, so those are our three big ones. Then we had all our rules for working with quantifiers. We had universal specification, universal generalization, existential specification, and existential generalization. And then we had our one new rule for working with identity that we introduced last time, I think, right? Rule I. Remember what that rule says?
Two things are identical, you can substitute.
That was half of it. One is
And
you can substitute equals for equals.
And everything's equal to itself.
And everything's identical to itself. Perfect. So last time, jumping down here a little bit, when we introduced identity, we introduced the law of identity, which is for all x, x equals x, or in other words, everything's identical with itself. And we introduced the principle of extensionality, which basically said that equals may be substituted for equals. It's one that told us we could do substitutions. And those two ideas were combined into rule I. And we did that last time. Okay, so there's a recap on our basic terminology and our basic rules of derivation. And then we started talking a little bit last time about theorems of logic. So, theorems of logic. What's the difference between a theorem and a theorem of logic? So before we were taking axiomatic systems, we started out with some set of axioms, and we proved what we called theorems in that system. What was a theorem in an axiomatic system?
was something that was tautologically implied by the axioms.
Yeah, it's something that the axioms implied was true. If the axioms implied it was true, we call that a theorem. So in general, a theorem, it's a logical implication of the axioms. Well, now we have a notion of a theorem of logic. What do we mean by a theorem of logic? That is a logical implication of that fancy symbol, the empty set. It's the thing implied by those axioms. Or in other words, no axioms. It's the things that we can assume in every single axiomatic system, because they're not dependent upon any axioms. They're just the things that just depend on logic itself. And since we can use logic in any field, we get theorems of logic for free. The things that are implied just by the rules of logic. No axioms. So the things that we can basically do, accepting these things up here. So those are just theorems of logic. And in every field of math, every field of science, every field of study, you can always use these theorems of logic. Now last time, we already proved a couple theorems of logic. The first theorem of logic that we proved is for all x, if x is equal, or for all x and y, if x is equal to y, then y is equal to x. Or in other words, we proved identity is symmetric. And we proved last time that for all x, y, and z, if x is equal to y and y is equal to z, then x is equal to z. Or in other words, we proved that identity is transitive. So these were two theorems of logic that we proved last time about identity. And now we're going to move on to some theorems that I told you we would eventually prove. So last time, we were basically given this by the author. The author says, hey, if you have there exists some predicate about x, that's the same thing as not for all x, not that predicate about x. And the author said, if you have for all x some predicate about x, that's the same thing as not there exists some x, not that predicate about x. And so we just introduced that, hey, you can swap these out. You can swap out a for all with a not there exists not, and you can swap out a there exists with a not for all not. And I told you we come back and prove it later. So we just said that we could do that. We made that appeal to your intuition. We used it a couple times. I told you we come back and prove it later as a theorem of logic. So now I'm going to prove those. That's what's next. All right, so I'm going to break this one up into two steps. I'm going to show first that this implies this, and then I'm going to show that this implies this. Remember, that's what equivalent means. Alpha is equivalent to beta means alpha implies beta, and beta implies alpha. So that's what I'm going to show. So first let's show this implies this. That's what this proof's going to do. So I want to show that if there exists some x such that p of x is true, then it is not the case that for all x, p of x is not true. If there's an x that makes it true, then not all x's can make it false. Alright, we're proving an implication. How do we always and forever prove an implication? We assume the antecedent, show that implies a conclusion. So I introduce the antecedent as a premise. There exists x such that p of x. We take that as a premise, only dependent upon itself. Now, I'm going to do proof by contradiction. I'm going to assume that this is false. I'm going to assume that this thing is false, which is what this is, and show that leads to contradiction. And therefore, this thing must be true. So, as my next premise, assume this is false. This is not for all x, not p of x, so I'm going to assume for all x, not p of x. The negation of this as a premise. You can get a contradiction from that. So, that's our next premise. Only dependent upon itself for its validity, line 2. Now, if I know that there exists an x such that p of x, if I know that there exists an x such that p is true for x, then we can call that x alpha. And that is existential specification, specifying the thing that made that thing true. Existential specification on line 1, that gives us p is true for alpha. But I can do universal specification on this, once again using alpha. If this is the case for every x, it definitely has to be the case for alpha. So I get p of alpha and I get not p of alpha. Contradiction. So I get not this by reductio ad absurdum. Sorry, this whiteboard has a lot of dead spots. I'm probably going to stop using it after today. So we get the negation of this thing right here. Now, what did we just barely prove? I showed if this is the case, then this is the case. So now we're going to use our rule of conditional proof to eliminate 1 as a premise. So we eliminated 2 as a premise with reductio ad absurdum. So now we were only dependent upon premise 1. And now showing this implies this enables me to get rid of 1 as a premise. And so now this implies this. Remember our rule for conditional proof. Our rule for conditional proof is if I show that all my premises together with alpha implies beta, that's the same thing as showing that my premises alone implies alpha implies beta. So it enables me to get rid of alpha as a premise. So I take all my premises, which was nothing, and alpha, show that implied beta, and therefore my premises alone, which is nothing, gives me that alpha implies beta. And so we're now dependent upon no premises, which makes the theorem of logic. We are not assuming anything to be true outside of just our rules of derivation. Cool. Let's do the next one. Next, I want to show that if it's the case that not for all x, not p of x, then there must exist an x such that p of x. Now this one's a little bit weird with how we start. Let's get bugging, because it bugs me. So first, we're going to introduce p of x as a premise. It's dependent upon line 1 and x is a flagged variable because it was free in the premise that we introduced it. Now, we do not have a restriction against existentially generalizing on a flagged variable or to a flagged variable. So going from here to here, I said that there exists x such that p of x, and what did I do? I replaced all my alphas in this equation with x's down here. There were no alphas. Replace all my alphas here with x's down here and put there exists x in front of it. So we technically didn't violate any of our rules. I existentially generalized on nothing and put there exists x there. Now, that probably bugs you, because it bugs me. More intuitive way to think about it is that if p is true for x, then there must exist an x such that p is true for x. And that might appeal to the intuition a little bit better. But we didn't violate any rules. And now I can get rid of 1 as a premise down here using the rule of conditional proof. I showed that this implies this. So rather than assuming this is true, I'm just going to assume that this implies it. Or now I just have that this implies this. Okay, that's the weird part of the proof is getting this. After that, it's much more normal proof. Okay, now, what's my strategy from here? My strategy from here is to prove the contrapositive of this. I'm going to show that not this entails not this.
Okay.
All right. So, I'm going to start with not there exists x p of x, and I'm going to end up with for all x not p of x. So not this implies not this, proving the contrapositive. All right, so not there exists x such that p of x, that's going to be a premise. Now notice that looking at the contrapositive of this, not this gives me not this. So from here to here, I get not p of x. Now notice that this was our premise, line 4 was our premise, and that x is not a flagged variable in our premise now. There's no flagged variable. So going from here to here, x is still not a flagged variable, which means I can universally generalize. And so if there does not exist an x such that p of x, that means for all x, not p of x. That's the thinking we got to there.
Okay.
All right, so we showed that this implies this. That's conditional, our conditional premise here. I showed this implies this, and now once again, I'm not dependent upon any premise. But notice that this is just contrapositive of this. So I take the contrapositive of this, that's right there. Which is what we were trying to prove. Contrapositive of this is right there. So this is tautologically equivalent to that line. And we have it. I showed that this implies this. And since I showed this implies that, I've shown it both ways now. I've shown this implies that and this implies that, or in other words, they're logically equivalent. Good? Can I see all the way over there? Yes. Okay, next. I want to show that these two are logically equivalent to each other. And I'm going to use this fact to do it, rather than proving it all from scratch. So I'm going to reference this fact. I'm just going to call this fact my theorem. So this is my theorem, THM. Sorry, turbo handwriting. Okay, so let's prove that this is now logically equivalent to this. I'm going to split this into two parts of the proof. I'm going to show this implies this, and this implies this, therefore they're logically equivalent. So first I'm going to prove the forward direction. I'm going to show this implies this. So assume this is my antecedent. There it is. It's a premise, only dependent upon itself or its validity, nullify variables. Now looking over here, this tells me there exists x such that some predicate about x is the same thing as not for all x, not that predicate about x. So I have there exists x, some predicate about x, is the same thing as not for all x, not that predicate about x. So I get from here to here, that's tautologically entailed by line 1, and what I'm going to call my theorem down here. So using that theorem. Now, obviously, all my nots cancel out. Not is the same as no not. Not is the same as no not. And so we get for all x, p of x. Pretty simple? Alright, so I just barely showed, sorry, this dead spot on the board. Not there exists x, not p of x, implies for all x, p of x. So I proved in the forward direction. Now I'm going to prove the other direction. I'm going to show that if this is true, then this is true. So this is now my antecedent, this is now my conclusion. I'm going to assume my antecedent and ultimately show that implies my conclusion. So as a premise, I didn't specify it here. When we switch this to the implication, that was using conditional proof, and so we're no longer dependent upon one as a premise. Okay, so now down here, again, we introduce for all x, p of x, that's as a premise, only dependent upon line 4 for its validity. Using our theorem once again, our theorem says that if you have for all x, the negation of some predicate about x, oh wait, first I'm going to add not signs, sorry. So here I have for all x, p of x, I'm going to put a not in front of the for all, not in front of the for all, and a not in front of the p of x. Which doesn't change anything. Two nots changes nothing. Now I'm going to use this identity. This identity says that if you have not for all x, not some predicate about x, that's the same thing as there exists in x such that that predicate about x. So I have, starting here, here's where I'm going to make my substitution. Maybe don't put that line there because that might be confusing. So we have our first not. I'm going to take not for all x, not some predicate about x, and replace it with there exists x such that that predicate about x. And then that not carries down right there. Substitution makes sense? So that's our substitution. And so I showed if you have this, then you have this. So using conditional proof, I say therefore this implies this, removing for as a premise. And so now we're dependent upon no premise. And so now I showed this implies this right here, and I showed this implies this right here. Combining those two facts together, we get this is logically equivalent to this. And again, dependent upon no premises. So that again is a theorem of logic. Okay, so that's my problems I proved to you. That those quantifiers, switching out those quantifiers like that works. And we're not breaking any of our rules. I told you some books, they just define the existential quantifier this way. And then we can still prove this the exact same way. They just define it this way, and they don't have our rules for existential specification, existential generalization here, because you can always write it in terms of just a universal. Some books do it that way. This author decided to introduce two more rules, and then we use those rules to show that this is still the case. So logically equivalent ways of doing it. It's just more standard, I think, to introduce this as a definition rather than having these two rules. But those rules are convenient, so maybe it's a better way. I don't know. Okay. our next theorem about logic. Our next theorem of logic, right here, what does it say? It says for all x, y, and z, if x is equal to y, then x, any operator, and z is equal to y, any operator, and z. So as a concrete example, if I know that x is equal to y in arithmetic, then I know that x plus 5 is equal to y plus 5. This implies this, and it is in no way dependent upon arithmetic for its validity. This is not, going from here to here is not something you would prove in arithmetic class or an algebra class. It's a theorem of logic. It's what we're about to prove right here. So circle is just a stand-in for any operation here. For any operation, as long as it's defined on the set, as long as x, that operation z, is something on our domain, then this is always the case. So let me give you an example of how we would break this. We might say, oh, if x equals y, then that must mean that x divided by 0 is equal to y divided by 0. Is that what this is saying? No, because y divided by 0 isn't in the domain. So this operator has to be well defined on the entire domain in order for this to work. Okay. But in general, it says you can add the same thing to both sides of your equation, you can subtract the same thing from both sides of your equation, you can multiply the same thing to both sides of your equation. As long as you're not dividing by 0, you can divide both sides of your equation by the same thing. All those rules that we use all the time in mathematics, they're never things you might have noticed if you think back to real analysis. We never actually proved those things. We just kept using them and we proved other things. We're going to prove the converse of this. We're going to show that if this is the case and this is the case, that's not a theorem of logic. That depends upon your specific field of math. But this to this is just a theorem of logic. So let's prove it. Again, what we're proving is an implication. What we're proving is an implication. We're proving if this is the case, then this is the case. And so, naturally, we start by assuming the antecedent. So assume the antecedent. This is a premise. And it's only dependent upon itself for its validity. Okay. X circle z equals x circle z. How can I justify that one?
The rule of identity.
Yeah, that's the rule of identity. Equals, how do you say it? Everything is equal to itself. So that is dependent upon no premises. We're the empty set. Right that way. We always know that's the case. That's just a rule of identity. Okay, so now getting from here to here, how do I justify that?
Also the rule of identity.
Yeah, I replace x with y. Remember, there's two parts to the rule of identity. One part is we can substitute equals for equals. So since x is equal to y, we can substitute x with y. And the other part of rule of identity is everything's equivalent with itself. So doing that substitution, we were using line 1 and line 2. We were doing a substitution of line 1 into line 2. And so this is dependent upon premise 1 for its validity, because we use line 1. And now, we showed that this implies this. So, using conditional proof, we're able to remove 1 as a premise.
Okay.
I should have specified up here that x and y are 5 variables, right?
Yeah.
Because they're free variables, they're not bounded. But we removed it, and so now down here we're not dependent upon any 5 variables, and so we can universally generalize. So this is universally generalizing on line 4. And again, we're not dependent upon any premises. So there we go, we proved it. Now, here's another rule that we use all the time. We're not going to prove this one because it's almost an identical proof. But what does this one say? It says if x is equal to y, then anything operation x is equal to anything operation y. That same thing over and again. So it's just swapping the order. And you do the exact same thing. You just swap the z's. Proof's identical.
Right.
So in other words, in math, we can add the same thing to the right-hand side of our equation or to the left side. If we add the same thing, it's still true. Or subtract the same thing from both sides. Doesn't matter if we subtract it from the right or the left. It works. Or multiply or divide or any other operation we have defined. Okay, so those are our basic theorems of logic. we won't be proving any more theorems of logic. I think that's all the theorems of logic we'll be using for the most part. And now, we're going to do some proofs in an axiomatic system where we need to use some of these theorems of logic. Remind myself that I'm still just on the chalkboard. Probably have to go to the whiteboard before this is all said. Let's see, roughly, what's the middle? Somewhere like right here. Okay. So now we're stepping into another axiomatic system as another example. This one, just in case you're interested, is called group theory. But we're only going to operate with 3 axioms. So, terminology. Let's have some, I'll write it here and then we'll erase it. What we call the primitives of our system, our primitives. Our primitives are the things that we're not going to define. They're the symbols that show up in our axioms. So one of our primitives up here is this circle operation. So axiom 1 says we have some operation, our circle operation, and all we know about our circle operation is it's associative. We know that x circle, y circle z, I may call it circle compose on accident, but it's just what I call it. So when I say compose, I just mean that operation. So x compose y compose z is the same thing as x compose y compose z. So that's our first axiom. We're just going to assume that whatever this operation is, it's always associative. Our second primitive is a constant e in our system. We are assuming that there is something out there, we're going to call it e, such that for any x in our domain, x composed with e just gives us back x. Make sense? E is some special symbol such that when we compose with it, when we compose anything with it, it doesn't change. And then finally, our last symbol is the inverse symbol. What does this say? Our last axiom says for every x, there exists, I may always read this as x inverse or inverse x. So for every x, there exists an inverse x, such that x composed x inverse is equal to e. Now, to help us get intuition about this thing, let's come up with an interpretation really quick. So one interpretation we could apply to this, we could assume our domain is just the numbers that we know and love, the real numbers. We could assume that our circle operation is really just plus. We could assume our e is really just 0. And we could assume our inverse is really just the negative sign. And so rewriting out our axioms, what is it saying? I'm going to not bother writing the quantifier part. I'm just going to skip straight to this. In our interpretation, we're saying that x plus y plus z is equal to x plus y plus z. We're saying that x plus 0 is just equal to x. And we're saying that x plus negative x is equal to 0. That's our interpretation. That's one interpretation. Turns out there's a lot of interpretations we can make for a group. Common one, I don't know if you remember from discrete math, permutations. Bijective functions on some set. Yeah. And you'd actually interpret that as function composition. You'd interpret that as the identity function. And then inverse would be the inverse of a function. As another example of something that satisfies these groups. So the real numbers, addition and 0, satisfy it. And then something completely different, permutations, composition, the identity function, and inverse functions satisfies this. So there's a bunch of different areas of mathematics that happen to satisfy these exact axioms. And so when I prove something just using these axioms, I'm simultaneously proving things that are true when we're talking about addition 0 in the real numbers. and things that are true when we're talking about permutations, compositions, and composition. So it's amazing what we're doing when we prove things from just these axioms. We're proving it for every possible interpretation of those axioms. Any interpretation you can come that satisfies those axioms, turns out the interpretations of all these proofs are going to do it. And so what is this one saying right here if we look in arithmetic? In terms of arithmetic, what's this one saying? This one's saying that if x plus y is equal to x, that implies y is equal to 0. Similarly, in terms of permutations, that's saying if the permutation pi composed sigma is equal to pi, that implies, or is equal to the identity function, then that implies, is equal to pi, then that implies that sigma is equal to your identity function, iota. So we're doing those things simultaneously. Every interpretation. Sorry, I can't think of another one that's off the top of my head that is a group.
Multiplication.
No, multiplication is not a group. What does it break?
Which axiom does it break?
So you have to think about a domain, right? So let's think about why multiplication doesn't satisfy this.
Okay.
So the first one says that, is it true that x times y times z is equal to x times y times z? Yep, that one's true. So multiplication is associative, that one works.
Mm-hmm.
What would our identity element be for multiplication?
Oh, it breaks the third one because
Yeah.
division by
Our identity element for multiplication would be 1, and it's always the case that x times 1 is equal to 1, so 1 would be our stand-in for e, but yeah, here's the one that's broken. For any x, there exists an inverse, such that their product is 1. Is that true? No. The one x that breaks it all is 0. And so if our domain were the real numbers minus 0, then now it is. If we got rid of 0 in our domain.
Right.
Sorry, that means everything except 0. 0 is the only thing that breaks it. And so then if we do that, then yes, that becomes another interpretation for this. And all these terms now work. Okay. So we've only got those 3 axioms. And from those 3 axioms, we're going to prove all these theorems. First theorem we're going to prove. We're going to prove what we call the right-hand cancellation law. If x compose z is equal to y compose z, then x is equal to y. Notice how that differs from the theorem of logic that we proved. The theorem of logic that we proved is going the other way. It was saying if x is equal to y, then x compose z is equal to y compose z. So we're going to prove it the other way, and we're going to see how proving it the other way requires us to use these axioms, and we couldn't have done it just using logic alone. Although it kind of appeals to your intuition that you should be able to do it just logic alone. At least it does mine. But if you try, you get stuck. Alright, so let's prove this. Proving theorem 1. And for the first, I don't know, maybe 2 of these, I'll do the proofs completely rigorously. And then after that, we'll just start seeing the connections and doing more half-hearted proofs. Okay. And so I'm going to use my notes here to make sure I don't accidentally skip steps. Okay. So theorem 1, what are we trying to prove? We're trying to prove that for all x, y, and z, x compose z equals y compose z implies x is equal to y. All right, that's what we're trying to show. Okay. Since it's an implication, natural place to start is assume the antecedent. So, assuming the antecedent, x compose z is equal to y compose z. And this is just a premise. Dependent upon itself, we'll just remember that one's flagged. I don't want to keep writing x, y, and z after it. We just know we need to get rid of one as a premise before we do any generalization. Okay, that's our first step. Now our second step here is using a theorem of logic. Oh, I'm combining two into one. No, we're fine. Okay. 2, if x compose z is equal to y compose z, that implies, so looking, here's what I'm going to use. If two things are equal, I'm going to use this version of it. If two things are equal, then I can compose both of them on the right-hand side, and they're still equal. So if these two things are equal, then if I compose something to both the same thing to both their right-hand side, then they're equal. And so that would imply, sorry, my implication arrow here is smaller. That would imply x compose z inverse is equal to y compose z inverse, right? I just composed the same thing to both sides. If those are identical, then if we compose the same thing on the right-hand side of both of them, it's still equal. So this is just using this theorem of logic. So this is not dependent, that's an empty set symbol, upon any axioms. Now I'm going to obviously combine this and this. This is alpha, this is alpha implies beta. Put those together and you can conclude beta, right? So then I know that x compose z inverse is equal to y compose z inverse. And now, this was tautologically entailed by lines 1 and 2, and we're dependent upon premise 1 for our validity. We still get rid of premise 1 before we're all said and done, because it has 5 variables. Okay. Oh, that's ugly. Writing out all our steps. Okay, now next thing I want to do is, remember what I'm trying to get. I'm trying to get x equals y, right? Jumping ahead, you could probably see what we're going to do. I know that I know that compose is associative here. So x compose z inverse. This is going to be the same as x compose z inverse. And what is z compose z inverse?
E.
Z compose z inverse, anything compose its inverse is equal to e. And what's anything compose e? Just that thing. So this is all just going to be x, this is all just going to be y. I'm going to get x is equal to y. But I got to write out all the rules as I use them. Maybe we'll only do this for the first time. Okay, so my first rule, or my next step here, is going to be observe that x compose z inverse, is equal to x compose z inverse. And that is using axiom 1, right? And 5, I'm saying, notice that y compose z inverse is equal to y compose z inverse. And that again is axiom 1. And now I'm going to use the law of identity on this line. I'm going to substitute x compose z inverse with x compose z inverse. So substitute this in for that, and substitute this in for that. And so I'm going to rewrite line 3. So rewriting line 3, we get x compose z inverse is equal to y compose z inverse. That was using identity on lines 3, 4, and 5. So I substituted in line 4 and 5 into equation 3. And that's what gave me that. All right, And what are the premises that we are dependent upon now? Since we used 3, we're now only dependent upon premise 1 and axiom 1. Premise 1 and then axiom 1 because that's the axiom we use in these 2 lines. Right? Okay, now I'm going to want to replace that with an E. Z compose Z inverse, I want to replace that with E. Before I can do that, I need to say that Z compose Z inverse is equal to E. That's using axiom 2. And now I can make that substitution into these. So 8, substituting Z compose Z inverse for E into both these, I'm going to get X compose E is equal to Y compose E. That is using identity on lines 6 and 7. And now we are using 1, axiom 1, and axiom 2. Right? And now I need to notice that X compose E is equal to X according to axiom 3. Oh, this was axiom 3, sorry. That's axiom 3. So this one is axiom 2. And maybe I'm not being clear. We're using universal specification on axiom 2. And universal specification on axiom 3. And universal specification on axiom 1. Every time we use the axiom, it's some combination of universal and existential specification, replacing our x's with x's and our e's with e's, and keeping all our symbols the same. So it's still not completely rigorous because doing all that real tedious. Okay, line 10. Using axiom 2 again, we know that y compose E is just equal to y. Anything composed with E is just that thing. That again is using axiom 2. And so now, substituting this in there and this in there, on line 11, we get x is equal to y. This was using identity on lines 8, 9, and 10. And now we are dependent upon premise 1 along with axiom 1, axiom 2, and axiom 3. Okay. And so what did we show? 12. We showed if this is the case, if x compose E is equal to y compose E, then x equals to y. So we showed if x compose E is equal to y compose E, then x is equal to y. That was using conditional proof, and now we eliminate 1 as a premise, and now we're only dependent upon our axioms. Axiom 1, axiom 2, and axiom 3. Axiom 3. Forget our last critics. Alright, and then we just universally generalize, and we're done. So 13. Then for all x, y, and z, if x compose E is equal to y compose E, then x is equal to y. And that was universal generalization on 12, and we're dependent upon the same axioms. Axiom 1, 2, and 3. So since we were dependent upon axioms when it was all said and done, this is not a theorem of logic. This is something that's only true in our system. And notice that we had to use all 3 of those axioms in our system. So in any system where we want this right-hand cancellation law, we need to make sure that that system has at least these 3 properties as axioms, or ways to prove them from your axioms. All right, there's theorem 1. Any questions on that before we go to theorem 2?
Well, I was wondering, are we not able to prove at all that x compose y equals y compose x from these 3 axioms?
You do not have commutativity in a group. And if you think back to function composition, it's not commutative.
Yeah.
So no, you should not be able to prove that.
Okay.
Although it does happen to be true for our plus operator.
Right.
Next theorem, theorem 2. And maybe before we do theorem 2, let's re-go over our thinking just to make sure it's clicking, but this time in terms of our interpretation. And maybe that will help all this click just a little bit better, what the logic was for each line. So I'm not going to write the premises and everything down, I'm just going to write the line each time, but in terms of our interpretation. So 1, we started out with the assumption that x plus z is equal to y plus z. Line 2 was, if x plus z is equal to y plus z, then x plus z plus negative z is equal to y plus z plus negative z. And then we combine these two things together, 3, to get, therefore, x plus z plus negative z is equal to y plus z plus negative z. And then we use the fact that addition is associative, so we ultimately got to the point, forget lines for a second here now, this is the same thing as x plus z plus negative z is equal to y plus z plus negative z. And then a number plus its negative is always 0. 5 plus negative 5, 0. 10 plus negative 10, 0. 100 plus negative 100, 0. 0 plus negative 0, 0. So any number plus its negative is always 0. So this simplifies to x plus 0, our identity element, or x circle e, x plus 0, same thing, is equal to y circle e, or y plus 0. And then x plus 0, that's just x is equal to y. And so in our interpretation, that's basically the logic that we followed through here. Helps the first few times to have both a concrete example of the system you're talking about as well as seeing it in the abstract. So we'll move over here to continue proving. Oh shoot, that means we won't be able to see the axioms. Move the camera. And maybe I'll just scribble the axioms in the top right hand corner here so that we can see them. So A1 was for all x, y, and z, x compose y compose z is equal to x compose y compose z. Our second axiom was this one with the identity? Yes. It was, there exists some element, the identity element, such that for any x compose the identity element, just spits back out x. Then axiom 3 was for any x, there exists an inverse element, such that when you compose them together, you get back out the identity element. Okay. Hopefully this marker right there. So now let's prove theorem 2.
We would be able to prove left-hand cancellation just as easily as we did theorem 1. Right?
No.
Oh, I guess
So
that's
we
not fine.
will prove left-hand cancellation, and the thing that's going to help us a lot is this right here. The fact that x composed with its inverse is the same thing as its inverse composed with x. So we need to do everything on the other side. And I don't know if being able to swap around identities is also going to help us.
Okay.
We were proving that for all x, x composed with identity is equal to identity composed with x. Okay. This one maybe won't write out all the steps as much. So starting out, looking at axiom 1, I'm going to plug into axiom 1, universal specification on axiom 1, like this. E compose x inverse is equal to E compose x inverse. That's my starting point for that. Okay. Next, I know that x compose x inverse is the same thing as E. So I know that E compose E is equal to E compose x inverse. Which gives me that anything composed with E is just that thing. Maybe write down our axioms as we do this. So this right here, we were using axiom 1. This one right here, we use the fact that x composed x inverse is our identity element. That was axiom 3. And now here, we're going to use axiom 2, which is identity composed with, or anything composed with identity is just that thing. So we get E is equal to E compose x inverse. Right? Mm-hmm. This was using axiom 2. Try to explain my thinking a little bit. Well, maybe go through it and then explain the thinking a little bit better. 4. Now I know what E is. E is the same thing as x compose x inverse. So this gives me that x compose x inverse is equal to E compose x inverse. And that was, again, using axiom 3. Right? And now what?
Now we can do right-hand cancellation.
Now we can do our right-hand cancellation. That was our previous theorem. Our previous theorem says that if x compose something is equal to y compose something, then that x and that y are equal. If x compose something is equal to y compose something, then my x and my y are equal. So then I get 5, then x is equal to identity compose x, and this was using theorem 1, right? Okay? But I was trying to get x compose E is equal to E compose x, not x is compose E compose x. Mm-hmm. So now what?
You can, well, we know that x compose E is equal to x from axiom 2.
Right, axiom 2 tells me x is the same thing as x compose E. So I can replace that x with an x compose E. So x compose E is equal to E compose x. And that was using, was that axiom 2? Axiom 2. So you can see we only depend upon axioms 1, 2, and 3 in all this, or on a theorem, which also, when it was all said and done, only depended on axioms 1, 2, and 3. So we're good in terms of that. We don't need to worry about, did we depend upon any premises that we needed to remove. So we know that we could universally generalize this. But, so what was the thinking here? The thinking I was after is I need to somehow get an E on the left side of x. That was my whole trick to this. So I knew that I needed an E compose x to come up there somehow, which is what made me think to start with this. And then from there on out, it was just keep messing with this until it was just an E again. And then I knew I could replace it with the x compose x inverse, cancel out the x inverses, and there we go. So I was just looking for something when I started this proof that had an E composed X in it. Somehow forcing that to show up. Ends on 7. Since we don't have any flagged variables or anything like that, we can obviously now universally generalize for all x. X compose E is equal to E compose X. And we're done. And that's about how formal I'll be with the proofs from here on out. Assuming that that was clear enough that there's no questions. Anything there we don't like? Well, if you love it, we'll continue.
Sounds good.
Alright, so theorem 3. Hopefully this marker doesn't die on me. Theorem 3. Theorem 3 is that for all x, x compose x inverse is equal to x inverse compose x. Okay, so again, this one's not an implication, so it's always a little bit weird to think, how do I start with proofs like this that aren't implications? Because I don't start by assuming my antecedent.
You can start with an axiom and then manipulate the other side to be what you want it to be or something like that.
Yeah, so for this one, I start out with the axiom. I'm going to start out with this one again. I don't know if it makes it clear if I do it a particular way on the left or the right. I'll write it the way I have it here in case it ends up mattering down the road. I might have gone back and did it for the sake of clarification. X inverse compose X inverse is equal to X inverse compose X inverse. So here we're using axiom 1. Notice that I just wrote it in reverse order, and I don't know if that really, if I thought that that would help clarify something down the road or not. But it doesn't matter which way we write it, right? Okay. So, let's see. Maybe probably should have done it that way. I'm trying to show that X inverse compose X is equal to X compose X inverse. X compose X inverse is the one I know how to do something with. I know what X compose X inverse is. That's E. I don't know what X inverse compose X is. So I don't know what this is, but I know what this is. So it makes sense why I wrote it this way. Because I'm going to manipulate this side of the expression. That's fine. That makes sense. So 2. I have no clue what this is. X inverse compose X. We're trying to ultimately prove that's the same thing as X compose X inverse. So we're leaving that side alone. But over here, I know what X compose X inverse is.
That's E.
E. Perfect. And now, what do I know I can do when I'm composing with E?
It's itself.
Well, what do I know I can, when I have X composed with E? What's something cool I can now do from the previous proof?
You can switch it around.
I can swap the E to the other side. So then 3, I can swap the E to the other side, and what's the great value of doing that?
Now you can do right-hand cancellation.
Now I can use my right-hand cancellation law, and I can cancel that out with that. So let's see, this right here we were using axiom, I think I'd have it memorized by now, axiom 2. Here we were using theorem 2, and now right-hand cancellation. So now I know X inverse composed with X is equal to E. That's using theorem 1. Now what?
Now we say that the left hand of that is equal to X compose X inverse.
So now X inverse compose X is equal to X compose X inverse. That's exactly what E is. And that's using axiom 3. Right?
Yeah.
And now, since we didn't introduce any premises and it's just all axioms and theorems, we didn't have any premise introducing flagged variables, so we know we can universally generalize to for all x, x inverse compose x is equal to x compose x inverse. Right? Any questions on that one? That was fun. So now we're on to Theorem 4. So Theorem 4 says for all x and y, if x compose y is equal to x, then y must have been equal to identity. To help us understand this one, let's rewrite it in terms of our interpretation. If I know that x plus some number y is still just equal to x, what must y have been? If x plus something just gives us x, you look in your bank account, you have $1,000. I say, okay, I'm going to send you a secret amount of money. You still have $1,000. How much money did I send you? $0. That means y is equal to 0. That's what we're saying up here. If x compose y gets you back to x, then your y must have been your identity element. Another way that we can say this is our identity element is unique. There's only one identity element. Anytime I added something to x and it ended up x, there was only one thing I could have added. So one identity element is another way that we might interpret this proof. We'll just mess with it. It's hard for me to think about what I was trying to do rather than just think about it up here. If I get stuck, we can look at my proof. All right. So this one we're proving implication. How do we typically prove an implication? Assume the antecedent, show that implies a conclusion. So let's start out by assuming that x compose y is equal to x. What am I trying to prove if that's the case? This was our premise, so we have to get rid of that line when it's all said and done if we want this proof to be a theorem. So we're going to assume that, and we want from that that y is somehow equal to e. So y is equal to, well, first off, what's the only thing we know y is equal to?
Y compose e.
Y compose e. Am I going to want to write it e compose y or y compose e? I think I'm going to want to write it e compose y. Okay. We can do y compose e first, I guess, since that's what our axiom gives us, and then use our theorem. So y is equal to y compose e, that's axiom 2. I think I'm going to want to move that around 3 and call that means y is equal to e compose y. And that was using this theorem, theorem 2. So now this was using theorem 2. Okay, now what do I know identity is equal to?
X compose x.
Sorry, I may keep calling that e identity because it's our identity element. E is equal to x compose x inverse. So this is the same thing as x compose x inverse compose y. That was using axiom 3. Okay. Now what do I know?
Compose is associative.
I know compose is associative. As a general rule, you probably have to use a previous theorem for the next theorem.
You can switch around the x and x inverse.
Right, I can swap the order of those things. Yeah. What does that help me do? That's going to help me associate my x with my y, which when I have my x associated with my y, I can make my substitution. So I want to get my x and my y together somehow, so I can use my premise up here, because I still haven't used this. Okay. So the only way I can use this information is if somehow I get that x and that y together. So that's my goal, stick them together. So then y is equal to x inverse compose x, compose y. That's using theorem 3. And then 6, using associativity, y is equal to x inverse compose x, compose y. That's using associativity A1. Right? And now, what is x compose y?
It's x.
It's x. So 7, now I know that y is equal to x inverse compose x. And now we have used this premise. So this is tautologically implied by 1 and 6. And so now I am dependent upon 1 at this line in the proof. Right? Now, what is x inverse compose x?
It's x compose x inverse.
Annoyingly, it's x compose x inverse. Maybe it would have been worth it to do a little side proof to say that that's also identity. So it's x compose x inverse. That was theorem 3. 9. Okay, what's x compose x inverse?
Identity.
Identity. So y is equal to identity. And that is axiom 3. And so what did we finally show? We showed x compose y equal to x implies y is equal to identity. And now we are no longer dependent upon this premise. So that was conditional proof. And so then we can generalize. And we can say, okay, so it's the case that for all x and y, that if x compose y is equal to x, then y is equal to identity. And we're done. That's supposed to be a box. That marker's getting a little dead. Do we already try this one? Not showing it better. Yeah.
There's got to be a bunch of ways to prove these theorems because you've proved it different for every single theorem than how I proved it in my head.
There's got to be several ways to prove any of these, yeah. What do you think between those two, the blue or the black?
Black works for me.
The black one works better? Okay. Hopefully it lasts. Theorem 5. Okay, theorem 5 is now our left-hand cancellation. So theorem 5 is for all x, y, and z, if z compose x is equal to z compose y, then x is equal to y, right?
Yeah.
Okay, so how are we going to start this proof?
Assume the antecedent.
Assume the antecedent. Pretty safe start. So we assume z compose x is equal to z compose y. Okay, and now what am I trying to show?
X equals y.
I'm trying to show that x is equal to y. So let's play with x. And then start out with x and say it's equal to, it's equal to, it's equal to, and hopefully get to y. So what is x equal to?
X compose identity.
It's equal to x compose identity.
Are we allowed to add things to the left, like compose on the left? Because I thought we proved it. It's like
Yes, we can.
the theorem on the middle. Oh, okay.
Yes, we can compose the same thing on the left of both sides if we want. Okay, let's do a couple steps in one. So x is equal to x compose e. What's that equal to? I know I've got to get the z's in here somehow. Right? Because somewhere along the way, I'm going to have to use the fact, I'm going to have to take an x compose z and replace it with a or a z compose x and replace it with a z compose y?
You can do E is equal to Z compose Z.
Oh, I see what you were thinking.
Yeah, the proof would be like 3 lines long. I don't know.
Huh?
Sorry, you're saying adding things to the left side?
Well, maybe just walk me through your thinking.
You just compose Z inverse to the left of that equation. And then you'd get identity on the left, and then you're done.
Let us think. Is there any reason why that's bad? I don't see why not. Okay, so you're saying from here to here, we can say then Z inverse compose, Z compose X is equal to Z inverse compose Z compose Y. And that's a theorem of logic. Theorem of logic says, we didn't bother proving that one out all the way, but it's right here. So, that's just a theorem of logic. And then we can use associativity. So we can call this Z inverse compose Z, compose X, is equal to Z inverse compose Z, compose Y. And then Z inverse compose Z is the same thing as identity. So that's identity compose X is equal to identity compose Y. And then identity compose X is just X, and identity compose Y is just Y. And then we can say, therefore, this being the case implies this is the case, and then universally generalize. See from there?
Nothing's wrong with that?
I don't know why.
Oh, okay.
We showed if this is the case, then this is the case. Therefore, we were no longer dependent upon this as a premise. Here to here, that's just a rule of logic. Here to here, that's just associativity. Axiom 1. Here to here, that's just axiom 3.
Yeah, I was just wondering
Here to
because
here is axiom 2.
like you could have done the same thing for theorem 4, and so it seems a little bit weird that that one sheet can be used in 2 different places to make the proof simpler. But I don't know, maybe it's just convenient.
So, you're saying do the same thing for theorem 4, compose
Just
X inverse to the left and then swap orders. Yeah, it would have been way easier. Yeah, so she's saying we could have gone from here. We could have gone X inverse compose X compose Y is equal to X inverse compose X. Some associativity to combine those two. And we basically end up with, from over here, identity compose Y is equal to identity. Or in other words, Y is equal to identity. And yeah, that would have been a lot cleaner. Yeah, I like that. Cool. Next one. Showing that the inverse is unique. That is done. For all x and y, if x compose y is equal to identity, then y must have been equal to x's inverse. Maybe again, write that as an interpretation to help us understand what that's saying. We're saying that if x plus y ended up 0, then y must have been exactly negative x. Okay. Oops, forgot to mark this. This is Theorem 6. Okay. So, this one, once again, is implication. So, assume the antecedent. And we want to show that implies a conclusion. All right. What do we want to do first?
You can literally do the same thing.
Do the same thing. Compose x inverse to both left-hand sides.
That seems so weird that you can do it through the theorem straight.
Maybe we should have taken the time to prove that.
Yeah, so we're using it.
And make sure that we didn't cheat. Let's just prove it as a side thing really quick, just to double check.
Fair enough.
So the theorem that we keep using over and over again is that if we're composing on the left-hand side, right?
Mm-hmm.
If x is equal to y, then z compose x is equal to z compose y. Using just logic, we should be able to start with x is equal to y, 2, yeah, it's definitely true. Z compose x is equal to z compose x. That's using law of identity.
I thought if two things are equal, then you can do an operator to the both of them and it's still equal. But by do an operator, does that mean z compose x?
So here's our premise. And then this is just using the law of identity directly. Everything is identical with itself.
Oh, sure.
And then, using the law of identity in its substitution form. You can substitute an x for a y. And so then I get z compose x is equal to z compose y. Yeah. Easy as pie, so. I can't imagine why we can't.
It just seems too easy to be true.
It does seem a bit easy. But maybe that's just because the first time we ever came across this stuff, for some reason we didn't think to do that. And so we just have in our head that these should be harder than they are. Because I don't know I've ever actually seen someone prove these things before.
Oh, shoot.
I think I've just done it. And you've probably just seen me do it. And so that probably gauged how hard you think it should be. Because I kept going through hard ways to do it. Anyways, compose x inverse to the left-hand side of both things. So then we get x inverse compose x compose y is equal to x inverse compose e. Then we get, using associativity, x inverse compose x compose y is equal to, using associativity there, over here, we're using the fact that anything composed with identity is just that thing. So a couple steps in one. So this is just x inverse. And then x inverse compose x is the same thing as x compose x inverse is the same thing as identity. Hopefully that's not too many pieces of logic in one go. So that's identity compose y is equal to x inverse. Or in other words, y is equal to x inverse. And so we showed this implies this, so now we're no longer dependent upon this as a premise. So we showed if x compose y is equal to e, then y is equal to x inverse, and then we can universally generalize from there. Cool. Theorem 7. Hopefully how thick I'm going is compensating for how bad the marker is. This one is that if you inverse the inverse, you get back to where you started. So this one is for all x, x inverses inverse is just x. Or in terms of our interpretation, we're saying that negative negative x is the same thing as x. This is the proof basically that negatives cancel out each other. Two negatives cancel out. In arithmetic, but we're not in arithmetic. I don't know why I slanted down so much. That looks awful. It's getting driving me nuts. For all x, x inverse inverse is equal to x. Okay. a little bit more sane. 1 proving this one. I say we just grab the bull by the horns. Let's just start with x and see what it equals. So I know always and forever, you can imagine that we're starting with x equals x as our starting point using the law of identity. That way we're not dependent upon a premise.
Okay.
But then I'm going to compose identity on it. Okay, and so now that's equal to x compose, and now I'm going to write identity a little bit funnier than what we're used to seeing. Identity is always some element composed with that element's inverse. Some element composed with that element's inverse. That's always what identity is. Identity is anything composed with its inverse. In this case, the thing I'm choosing is x inverse. So x inverse composed with x inverse's inverse is always identity. Make sense? And then this is just equal to associativity. So rather than associating these two together, I'm going to associate those two together. So that's equal to x compose x inverse composed with this thing, x inverse's inverse. But now x composed x inverse is identity composed with x inverse's inverse. And now identity composed with anything is just that thing. And so we get x inverse's inverse. And we weren't dependent upon any premises because our starting point was just the law of identity. X equals x. And then from there on out, we were just using axioms. Right? And probably some theorems for swapping orders on things. Cool. Next theorem. Theorem 8. Let's see. Theorem 8 is saying for all x and y, there exists some z such that x is equal to y compose z. Okay. All right. How should we start this one? We need to show that for any x and y, we can find some z such that when we compose y with that z, we get x. Let's think about this in terms of arithmetic for a second. I'm saying come up with any two numbers you want. Something like 11 and pick a y. 2. We're saying that we can always find some z that satisfies this equation. In this case, what's the z? 9. How did you get 9?
11 subtract 2.
11 subtract 2, or another way to think about that is 11 plus 2's additive inverse. So you said the z that was going to work was 11 plus negative 2. Let's see if that generalizes. If we would have instead did something like 57 here and negative 6 here, and now what's the z? Is the z still 57 plus negative 6? Well, negative 6 is just 6. 6 plus 57 gives us 63. 63 minus 6 gives us 57. Yep, it works. And so in general, what are we doing? We're saying that if this is x and this is y plus z, we're saying z in general is equal to x plus y's additive inverse. Right? And now going back out of our interpretation. So sometimes that's just a useful thing to do when you get stumped on these. Come up with the interpretation, find a pattern in terms of your interpretation, and then go back out of your interpretation. So now reverse engineering back into our system here. We still have z, we still have equals, we still have x, but instead of plus, we have circle. And instead of negative y, we have y inverse. Right? So, that's exactly what we can do. We can let y, or let z, equal x compose y inverse. Then, y compose z is equal to what? And we can figure it out from here.
We're just saying let x and y be any number, and then let z be a number such that it's equal to x compose y inverse?
Yeah, if we were writing out the mathematical version of the proof, we say let x and y be any two elements, and observe that y has an inverse. Let x be whatever x compose y inverse is. Or sorry, did I say that right? Let z be whatever x compose y inverse is. And now let's look at y compose z. So yeah, let z be this thing. We know that this thing is some element in there. So what is y compose z? That is y compose z.
But we don't have a theorem that lets us switch things around yet, do we? Oh, we can't have that, that's right.
Shoot. Would have worked if we would have done it this way too. Y inverse compose x. So that's what is actually going to be our thing. It's because we were thinking in terms of addition, which was commutative, so it didn't matter what order.
Right.
But if we were thinking in terms of permutations, the order would have definitely mattered there.
Right.
And so z, we're going to say is y inverse compose x. So let z equal y inverse compose x, and observe that y compose z is equal to y compose z is equal to y compose y inverse compose x is equal to identity compose x is equal to x. And so we found a z that works, namely this one. So there does exist some z that satisfies this, and that z happens to be y inverse compose x. We want to try and do that? Maybe not. Maybe we'll just do the last one. We're getting close to informal proofs anyways. That'll be in the next section. So, our last theorem.
This isn't informal?
No. We're gradually working our way to it. The next section, that's a lie. The next section is a section that is just on the difference between an object and the name of the object, which we're going to skip.
Okay.
And it's the difference. So the example is, an example would be, Mom has 3 letters. Might make you think that Mom's playing a game of Scrabble and she's holding 3 letters in her hand, versus Mom has 3 letters. Now I'm talking about the actual word mom. So the difference between the actual object and the thing naming the object. That's what chapter 6 is all about, which I'm going to skip. because I don't think that's very productive.
Okay.
And then chapter 7 is on informal proof. And so the author then tries to slowly work you from, we're already getting pretty informal. When he does any of these proofs that he does, I'm not sure which ones he does it a lot closer to how we did this first one every time.
Oh, okay.
So he's still plugging and chugging everything as he goes. We're getting lazier and lazier. And then so section 7 is dedicated to going from full-fledged rigorous proofs to basically how we do proofs in math class.
Okay.
And it's making that transition. And I'm not going to bother going through all the discussion that he does to try and make it appeal to the intuition. He really drags it out. I'm just going to do the proofs that he does and do the first one rigorously and then show you how it would be done informally and then do them all informal after that.
Okay.
Because I think getting informal proofs seems the best way to get a feel for it. See it done both ways and see the contrast rather than someone trying to slowly walk you through all the intuition. Because a lot of that just kind of goes over your head when you're first coming across proofs and you just need to get comfortable proving and reading proofs. I don't know. And that will be with the axioms of arithmetic. So next time we'll flat out just be doing something similar to this again, but with just all the axioms on arithmetic now.
Oh, okay.
Which is a much more full system. And then after that, theory of definition, and then set theory.
Nice.
Getting close. Anyways, theorem 9, our last theorem of the day. For all x and z, there exists a y. This one is for all x and z, there exists a y such that x is equal to y compose z. So for any y, we could have found something to stick to the right of it to give us x. Now we're saying for any z, we could have found something to the left of it to give us x. And so, what is our y going to be? What's the thing that we could stick right here that would give us x when we compose it with z?
X compose the inverse?
X compose y inverse. Or z inverse. X compose z inverse. That's going to be the thing. So if y equal to that is going to be our magic number. And so what do we get? So we get y compose z is equal to, make that substitution for y. That's x compose z inverse. There's our substitution for y. Compose z. Use associativity, that gives us x compose z inverse. Now z compose z inverse is identity, so that gives us x compose identity. Anything compose identity is just the thing itself, and so there we have it. We found something that would work for us. Okay, and that's it. That's going to be the end of our dive into group theory. We won't go any deeper than that. Group theory is just the axiomatic system when you start with these three axioms. The same way that arithmetic is the one starting with the axioms on arithmetic, which we will start next time. We already did a review of logic. I don't think we need to do another one. So, yeah.
That's if the people watch the video.
Even if they don't, I mean, it's a fresh start.
True.
It's just easier to start with something like group theory where you only have 3 axioms rather than arithmetic where we have 15 axioms.
Oh, that's right.
Yeah, because you have to state addition is associative and commutative, and there's an additive inverse, and there's an additive identity, then all that with multiplication, then your distribution laws, then your laws for the less than symbols, and then finally, 1's not equal to 0.
We did that in discrete math, right?
No, we did that in real analysis.
Oh, that's right.
Because real analysis,
Start with axioms.
start with the axioms on real numbers. You start with arithmetic,
That's right.
go from there. So yeah, basic arithmetic will be next week. Don't think we needed to say anything else about this. Maybe make one more note of what we call the primitive symbols of the system. Coming back to this, the primitive symbols were the constants and the operators and the relations. This one we didn't have any relations. Sorry, not relations. Predicates. A relation is a special type of predicate. So it's the operators, the constants, and the predicates that show up in your axioms. Those are going to be called your primitive terms. So in terms of this system here, we had three primitive terms. We had the circle operation, the inverse operation, and then the identity element. And those were our only primitive terms. So that's more terminology that you need to start getting comfortable with. So that when I say primitive terms, when we get further down the road, you know exactly what we're saying. The terms, the constants, operators, and predicates introduced in your axioms. Those are primitive terms. Because when we get to definitions, your definitions have to start out in terms of your primitive terms.
Wouldn't equals be a predicate?
Equals is a predicate. That's true. The same way that and or are operators, are logical operators.
Well, they are logical operators, so what do you mean the same way?
This is not, if none of these happen to use any logical operators, but our axiom, some of them could have had an and or an or in it. So, yes, it's using that logical operator, and it's technically a kind of operator, but it's a symbol of logic, and so it's not one of your primitives of your axiomatic system.
Equals is a symbol of logic, is what you're saying?
Equals is now a symbol of logic, because we're now in propositional and first word predicate logic with identity.
Right, okay.
If we weren't, like if we went back, I think we used identity back when we were like doing the preference axioms. There equals was just a predicate.
Okay, makes sense.
So now, since the logic we're using includes identity, identity is now treated the same way that logical operators are treated, in the same way that quantifiers are treated. Good question. Anything else? Cool. We'll end it there, and see you guys next week.